Hello, welcome again. In the last flip lecture, we looked at how we can study the response in two regions of time, the transient region and the steady state region. Also in the last flip lecture, we looked at different performance specifications that we can define for the transient region of the response. For control systems, there is one important specification in the steady state region of the response, which is the steady state error. Most control systems, most feedback control systems are made in order to ensure that the output tracks the reference or the desired input as much as possible. So if the reference is the input to the feedback system, RT, and YT is the output from the uh, system, then we would like the output to be as close to the reference. So we would like that the output approaches RT as t tends towards infinity, or limit t tends towards infinity, r minus y is equal to 0. If it is not equal to 0, so in general, let's say if we apply, say, a constant input r, and we get some transients, and then we settle down at some steady state value. If this does not approach 0, it approaches some value as, let's say, r minus y, which is steady state error, ESS, then this ESS is the steady state error or the tracking error. So E, the tracking error signal, is defined as ET is equal to R minus YT. Notice over here that this E should not be confused with this E, EA, which you get in the feedback system. If your Y is measured through a sensor which has a transfer function, which has some of its own dynamics, then this signal is not going to be same as a tracking error. However, if we assume that the feedback transfer function Hs is equal to 1, in that case, EA, this signal is just going to be equal to Rs minus Ys if Hs is equal to 1, in which case this EA signal will be same, this EA signal is going to be same as the Laplace transform of the tracking error signal. The steady state error is defined as the value of the signal E as t tends towards infinity. So this one, we can look at the properties of the Laplace transform. So if you look at the table for the Laplace transforms, which is given on the page 4 of your course book, you will see that there is a final value theorem which is provided to you, and it states that this signal can be related to limit s tending towards 0 s times Es. You can also find that there is a note which is written on this final value theorem, which says that this theorem is valid if all the roots of the denominator of the signal, which is Es in this case, must have negative real parts and no more than one can be at the origin, which is a mathematical way of saying that this Es should be a stable signal. So it should approach some steady state value. This theorem is going to give you a wrong result if ESS is an unstable signal or it goes to infinity. So you may still find that this value approaches to some constant value, but that result will be wrong. But don't worry, in this course, usually we are supposed to make a check about by looking at the ES, but in this course, all the systems that we are going to encounter are going to be stable systems. So in this course, you will not encounter the applying the final value theorem to systems which are unstable to begin with. So in order to find out what this ES is, we can replace ES by the Laplace transform of this equation. If we replace it by the Laplace transform of that equation, we get s times Rs minus Ys. Then the limit of s tending towards 0, we can We can pull out the RS out of this bracket. So we end up getting S times RS over 1 minus y divided by RS, where this is represented by T, which is basically the same as the closed loop transfer function, which we have also encountered earlier. So this we know that we have found that this closed loop transfer function, uh, we studied the formula for this earlier, was given by the forward loop transfer function G over 1 plus for negative feedback system, so plus G times H. So this ends up being the steady state error. So let's look at how to apply this to look at the steady state error for systems, for different feedback systems to different inputs. So let's look at it through example. So over here, you can see that the example is asking for finding out the steady state error of the system first to a step input of magnitude 2 and then for a ramp input. So let's try to do it for the step input. So in this case, we are looking at an input R, RT, where it is 0 for time t less than 0 and value of 2 for t greater than 0. So in this case, this Laplace transform, Laplace transform of RS is going to be Laplace transform of 2 times the step function, unit step function, which is basically 2 over S. We can also find out that the closed loop transfer function, Ts, in this case, is equal to Ys over Rs is equal to, applying this formula, we can see H is equal to 1. So this is a unity feedback system. So G over 1 plus G, which ends up being 1 over S plus 3. So steady state error ESS is equal to limit S tending towards 0, S times RS 1 minus TS this ends up being limit S tending towards 0, S times 2 over S, which is the Laplace transform of RS, over times 1 minus 1 over S plus 3. So you can see that the S in the numerator cancels with the S in the denominator. We end up getting limit S tending towards 0, 2 times S plus 2 over S plus 3, which is equal to, we can now, since there is no S in the denominator, this is not an indeterminate system, we can simplify this as 4 over 3 by replacing S with 0. Therefore, in this case, the steady state error is equal to 4 divided by 3. So I can tell that in this case, when I apply a constant input of 2, starting from time t is equal to 0, my output response is going to have some transients, and then it will settle down at a steady state value YSS such that this YSS is 4 by 3 lower than the value of 2. Or in that case, I can also describe that my YSS, if I was trying to find out what my YSS is going to be, so I can basically describe that this is going to be equal to 2 minus 4 by 3. So basically equal to 2 by 3. So this is not asked in the problem, but you can find it out based on your understanding of the system. Also notice that I took a non-oscillatory response over here. I basically showed that I just increased from the value of 0 to the steady state value. This is based on my understanding of how systems such as this transfer function, so systems such as the transfer function which is described by this system behave. So you will also have this understanding by next week of the lectures. So the next problem is asking about what happens when we apply a unit ramp input. So in this case, unit ramp input unit ramp signal RT is equal to T, or RS is equal to 1 over S square. In this case, you can see that steady state error ESS is still going to be limit S tending towards 0, S times RS 1 minus TS. So this portion 1 minus TS still remains the same, but now I end up having limit S tending towards 0, S times 1 over S square, S plus 2 over S plus 3. So one of the S in the denominator cancels with the S in the numerator, but now we can see that in this particular case, this limit approaches to infinity. So this infinity steady state error means that S time t is approaching infinity. The reference signal and the output signal are diverging. So in this case, we applied a ramp signal, a unit ramp signal. So this has a slope of 1. So this had a slope of 1. Based on my understanding of the system response, I can say that the output signal starts off by from 0. So basically it picks up the speed, but then it starts, it goes and increases over time. It is still trying to track the reference, but the slope of this is going to be less than 1. So basically, as RT is going towards infinity, YT is also going towards infinity, but the steady state error, because the slope is less than 1, so this ESS is also growing over time. Notice that even though both RT and YT go towards infinity, if the slope of YT was equal to 1, if the slope was same as that of the reference signal, then we could still have a constant steady state error as t tends towards infinity, but that is not the case in this case, in this particular one. So it can happen in some other systems, but it did not happen. It doesn't. A constant steady state error for a ramp input did not happen for this particular system. Next, we'll look at the concept of a type number. Something to note over here is that this is only valid for unity feedback systems. So type number, we can also make some decision about the steady state errors based on the type number of the system. So whatever I'm going to describe to you next can only be applied when the transfer function on the feedback side, which was basically HS, when HS is equal to 1. So do not, if you see any other transfer function, so if you see any block with a transfer function not equal to 1, then whatever I'm describing over here cannot be explained. You can still define the type number for non-unity feedback systems, but the description I'm going to describe later on is not valid. You have to, then the description is, then how you find out the type number is a little bit more involved. Okay, so in this case, we are looking at the, so we are describing the steady state error from the closed loop system. But in order to do that, we are looking at the type number by looking at what the transfer function G is, which is the open loop transfer function of the system. So G is what fits only on the forward loop side. And this G is basically written down as some numerator, K times some numerator, which can be expressed as a product of individual terms coming from zeros, divided by some poles where n number of poles are at origin, and then some other terms are coming from poles at locations not at the origin. So the type of this system, this transfer function is said to have a type number n for this particular one. So basically, the only thing that is important is the number of poles at the origin. So let's look at this example. So in this particular case, if we have this as the open loop transfer function, which can be expressed, the denominator can be expressed as s into s plus 1 into s plus 2. There is one pole at the origin. So this has a type 1. This is a type 1 system. So if we have a type number of the system as 0, what we observe using the final value theorem is that for a step input, we end up having a finite steady state error. For a ramp input, we end up having an infinite error. And similarly, for parabolic input, we also end up having an infinite steady state error. So let's look over here. So in this case, so in the problem that we looked at some time ago, here, if we look at the transfer function of G, so we only have to look at Gs is equal to 1 over s plus 2. For this, there are no poles at the origin. So this is a type 0 system. For a type 0 system, we saw that the steady state error was equal to 4 divided by 3. We can observe from the table over here that for a step input, we have a constant steady state error like we calculated in the previous case. Also, we calculated the steady state error for the ramp input using the final value theorem. So we use the formula in order to find out that the steady state error was equal to infinity. Instead, we could just have looked at the table. We could have just looked at the result from the table, which is not provided in your exams. So if you use this, you have to memorize it. So from the table, we can see that for the ramp input, a type 0 system has an infinite steady state error. So that could have been a shortcut way of describing that since the system is a type 0, then we have an infinite steady state error. We can see that as the type number increases, the steady state error decreases for the input. So basically, if we have a constant, as we go to a type number 1, the step input has a zero steady state error. So it decreased for a type 0 from finite to 0. For a ramp input, we go from an infinite steady state error to a finite, and for a parabolic input, we still remain the same. For a type 2 system, we have for a step and a ramp input, we have zero steady state error, while for a parabolic input, we have a finite steady state error. So at least when we look at the steady state error, having a higher type number is better for the reference tracking. So better for reference tracking because our steady state error approaches zero. One of the practical difficulties that we have is that as we go to a higher type number than 2, so if we look at systems, with type number greater than 2, it is very difficult to stabilize those systems. So even though we have a better reference tracking, but we end up having difficulty in the transient response. Basically, the response, the transient response is not a stable one. We never end up having a good. So we basically never end up reaching the reference value in the first place. So while it is good to have a system with a higher type number for reference tracking, but there are issues. There are some trade-offs that we face in terms of stabilizing the system. So we have to be concerned about those as we go to systems with higher type numbers. Okay, let's try to see if we can apply this kind of a table, and we can look at some of the problems. So we will try to analyze these problems, and these problems are also going to lead you to the different control actions that can be applied for feedback systems, which Carl is going to cover in the week 4 of the lectures, or week 5 of the lectures. So the first one. So we are looking at the plant 1 over s plus 2, and we are considering a controller which is referred as the proportional controller. So in this case, we call it as a proportional controller because if you look at the controller which is KP, so in this case, you can say that the control law is basically that what is the relationship between the input and the output of the controller. So in this case, the output of the controller, which is the actuation signal US, is just proportional KP times the input that goes inside the controller. So KP times EA. So controller just acts like a gain between the EA signal and the output. So if we take the inverse Laplace transform, we can also see that in the time domain, we also end up having just a proportional relationship between the input to the controller EA and the output from the controller U. So if you are trying to look at the type number of the system, so we have to look at the open loop transfer function. So open loop transfer function for this system, which is G, is equal to GC times GP. So controller transfer function times GP, which is KP over S plus 2. So this one has got no pole at origin. So this is a type 0 system. Therefore, if we apply a step input, then we have the steady state error for a step input is basically a finite value. So it is higher than 0, but between but not infinite. So we can find out that steady state error now using the final value theorem, using the formula that I described earlier. So in order to apply the formula, we find out the closed loop transfer function, which is basically T is equal to G over 1 plus GH. In this case, H is just equal to 1. So we end up getting this is equal to Kp over S plus Kp plus 2. So from the formula, we end up getting steady state error is equal to limit S tending towards 0, S times Rs 1 minus Ts, and that ends up being limit S tending towards 0, S times for a step input. So here we are looking at step input. So here Rs is equal to 1 over S. So we end up getting 1 minus Kp over S plus Kp plus 2, which ends up being equals limit S tending towards 0. So S in the numerator cancels with S in the denominator. We end up getting S plus 2 over S plus Kp plus 2, which is nothing but 2 over 2 plus Kp. So we can see that for this kind of a system, if you're trying to adjust a knob for the proportional gain and we want a better tracking, so we can see that if we increase the proportional gain, we end up getting a lower steady state error. So for this kind of a system, as Kp increases, steady state error decreases. So it will not go down to 0, but if we are happy with having a low enough steady state error, so let's say for some system we were trying to do a position control, we see an error of 1. We increase the proportional gain, we get so from 1 meter, let's say the position error decreased down to 1 centimeter. If we are happy with 1 centimeter of position error, then fine, we don't have to do anything else. So we have selected our proportional gain. So in this kind of a system, we can increase the proportional gain and decrease the steady state error, but we can never completely eliminate it. Next, let us take a look at the same plant being used in the system, but a different controller. This time, Gc is equal to Ki divided by S, and this is referred as the integral controller. In this case, the relationship between the output of the controller to the input of the controller, U is equal to Ki divided by S times E. So inverse Laplace transform, if we take the inverse Laplace transform, we find that U is nothing but related proportional to the integral of the error signal, which is basically the EA signal. In this case, EA is same as R minus Y. So being a unity feedback, EA is also representing the EA signal is also representing the tracking error signal. So in this particular case, so this controller, because the actuation is proportional to the integral of the tracking error, is also referred as the integral controller. In this case, if we look at the open loop transfer function, GS is equal to GC times GP, which is equal to Ki over S into S plus 2, which has one pole at the origin. So in this case, this is a type 1 system. For a type 1 system, if we look at the table, for a step input, we can see that a type 1 system has a zero steady state error. So as the problem said, we have to find out the steady state error for a unit step input. In this case, we find out that steady state error is equal to 0. So while the proportional controller was only able to make the steady state error small, the integral controller is able to make the steady state error equal to 0. So it is able to eliminate the steady state error from this plant. So uh, that is like if we want complete tracking, if you're not happy with the small enough steady state error, we want to completely eliminate, then we have to go to the integral controller. But notice that in many engineering problems, uh, you can never really define zero steady state error. So it's not practical to get zero error in engineering for many reasons, because of the problems with the measurements, because of the effect of disturbances, and so on. It's quite common in many practical applications that we combine the proportional and integral control action into a single controller, where we have the effect of both. We basically have the control action which is both having a term which is proportional to the error and proportional to the integral of the error, and this is referred as the PI controller. I'll let you find yourself what is the steady. If we so I encourage you to do the problem yourself, in which GC is equal to a PI controller, and then in that case find out what is the steady state error for a step input. So show that in that case also we end up having a zero steady state error. So I'll end the flip lecture over here. Thank you.